some of our work in thiochemistry. A little bit of an introduction and table of contents, what we'll be talking about today. First, we'll go over a table introduction. So we'll briefly discuss climate change in wine. That's been a big topic today, so that's lovely. You've already been introduced to that. Then we'll talk about current evaluation of smoke-affected wines and our methodologies behind that, and then other detoxification pathways. Then I'll follow up with some current research that we've been doing, so some identification of thiophenols in smoke-affected wine, and then also thiophenols in whiskey. Then we'll look at what our next steps are from there. So since 2003, smoke-affected wines have been a big issue across the world. It's not just here in the Yakima Valley, but also in Napa, Adelaide, and also Okanagan Valley. In 2020, about $3.7 billion of losses occurred across the US caused by smoke. This is going to be increasing as the years increase because rising temperature increases the risk of drought and prolonged ripening seasons. Increased risk of smoke exposure is greatly there no matter where you are in the world. We've talked a lot today about different volatile phenols, much like glycol, p-cresol, and phenol. All of these are really big. The concentration of these phenolics are in the micrograms per liter, but we're missing something when it comes to the ashtray flavor. We've identified thiophenols as playing a role in that sensorial effect. The difference between thiophenols and volatile phenols are the sulfonated compounds, and this makes them extremely reactive and harder to identify. Due to the sulfur in the structure, they are extremely reactive. Thiols are known to have some of the lowest odor detection thresholds identified in nature. And so once we add that into our complex matrix of wine, it gets way more complicated to identify. Because of their sulfonated nature, they're easily oxidized into more stable disulfides. This makes it a moving target to figure out what we're trying to look for. Recently, we've always been talking about the glycolysis. Wow, I can't say that word. Glycosylation and how that acts as a detoxification pathway for our volatile phenol. In wine, we do have our glycosides, but then it hydrolyzes in the bottle, releasing those different glycols, phenols, and other undesirable aromas. However, that's not the only detoxification pathway present in grapes and other plants. We have glutathione. Glutathione conjugates all these other toxic compounds and makes them more soluble in the vacuole. Glutathione is a tripeptide made up of 3 different amino acids: glutamate, cysteine, and glycine. These different amino acids, when they come together, work as a detoxification pathway. Glutathione binds to the strong nucleophiles and react with the soft electrophiles. The glutathione conjugates get stored in the vacuoles, much like the glycoconjugates. When it comes to glutathione, it's a precursor for many different thiols. Many thiols are very desirable in our white wines, much like Sauvignon Blanc. We do have 2 characteristic thiols that are really prominent in those and that have desirable aromas, much like 3-MH, which has it's the grapefruit aroma, and 4-MMP, which smells like boxwood. We wanted to evaluate how these different compound classes affect the aroma of wine. In 2023, we worked with Dr. Tomasino down at Oregon State to evaluate how thiophenols and volatile phenols work together, if they're having any sensorial relationship. For this project, we took a model-based wine, and then we spiked it with a low amount of volatile phenols, a low amount of thiophenols, and then we put them together to see how each one works together. If we look at our Grenache, it is spiked with both phenolics and thiophenols, and these both correlate with our ashy and smoky aromas. However, in that study, quantification was not possible due to the low concentrations that were available for us to use. We used about 5 nanograms per liter of thiophenols to spike those wines. When we're working in a real wine matrix, that can cause some issues. We're going to need a highly sensitive and specific method to be able to identify and target those different compounds. Because these different compounds are in very, very low concentration, targeted methods can be very limited. You might be missing some of the compounds due to them being in their disulfide or sulfide or their free form. In order to evaluate how these different compounds work together, we turned to a model matrix. We looked at Scotch whiskey and did a survey. Why we use Scotch whiskey is because during the malting process, peat is used to germinate our barley. And during this germination process, traditionally, it's exposed to a lot of smoke, and the level of smoke determines how peaty it is. And a lot of these volatile phenols then get absorbed back into the grain. Here is a picture of floor malting where they light the peat on fire on the bottom, and then the smoke rises, and this helps germinate. After germination, fermentation occurs, and then distillation. Distillation is a concentration step. So we're removing a lot of the background noise that we would see in wine or in beer, and we're concentrating it down to a more stable matrix, which makes it a lot easier to look for these thiophenols. These thiophenols favor alcohol, so this concentration step is very helpful in that. For our commercial survey, we evaluated 55 different whiskeys using GCMS for both thiophenols and volatile phenols. We looked at 35 different Scotch whiskeys, and we classified them based off of the distiller's classifications. So we looked at 15 heavily peated Scotch whiskeys, 20 moderately to light peated whiskeys, and then bourbons, because those are not exposed to any peat. We wanted to evaluate how the peat would affect the whiskeys and compare it to a more neutral grade. This principal component analysis describes 65% of the variance in the data set. It's a little hard to see, but most of our heavily peated whiskeys are all grouping together near the P cresol, M cresol, and our guayacols. If we look on the other side of the PCA, we can see that most of our bourbons and our lighter Scotch whiskeys are more associated or not associated with any of those smoky compounds and more associated with transoblactone, so more of a creamy aroma. When we evaluate the different individual compounds, we can see statistical differences between each set of whiskeys. There are 3 compounds that show complete statistical differences, which can be used to verify and differentiate the different groupings. So guaiacol, P cresol, M cresol, and furfural were also used. Furfural isn't shown on this graph because the concentration of furfural is extremely large and compared to many of these compounds shown here. Now, when we look at thiophenols, it's a little bit different of a story. We can see that all of our heavily peated Scotch whiskeys are associated with all of our thiophenols that we evaluated. We evaluated 6 different thiophenols using a single quad GCMS. Because these whiskeys are concentrated and these thiols really like alcohol, it's possible for us to evaluate them in this type of matrix compared to those in a lower alcohol matrix like wine. All of our non-peated or lightly peated whiskeys are not associated with any of our thiophenols. So this indicates that yes, there is a role that they play. When we look at the individual thiophenols, we can see that there are some that can statistically determine the differences between the styles of whiskeys. So thiophenol is one of the main phenolics that can contribute to the differentiation between styles. When we use a linear discriminant analysis, we're grouping all of these based off of their different styles, and we're able to differentiate them almost completely. Before, when we look at all of the different volatile phenols, they all kind of overlap. This indicates that they're not different. However, now we can use both of these compound classes to identify differences between different whiskey styles. This could be used for authentication of different whiskeys because that can be a big issue. Now that we've looked at a more simple matrix, we can move forward to use wine in a more controlled way. We've learned from these projects on different analytical methods that would be better to identify our precursors. We want to, moving forward, we want to identify different smoke-related precursors related to thiophenols. So we want to look for glutathione in our smoked wines and in our grapes as we're exposing them during our intentional smoke. We can also evaluate the kinetics of the smoke compounds accumulating within the different berries and see how that affects the different detoxification pathways. We also want to understand how these compounds evolve during fermentation. This could give insight into other mitigation techniques. I'm so sorry. Thank you so much. If you guys have any questions, please ask. Plenty of time. It's so much.
Thanks. Do you see any question? Sorry, go ahead.
What is your limit of detection at the moment?
If it depends on the concentration in which method we're using, when we're using general SPME, it's a lot harder to get my limit of detection down to the sub nanogram per liter. But we're currently working on additional methodologies to get that limit of detection a lot lower.
A lot of distilleries use big copper stills. Do you see any degradation in like sulfur compounds in those, or?
We haven't looked at the different parts of the copper still yet, but all of these products that we looked at were purchased within the.
They're clearly in there.
Yeah, they're clearly within the product if we're still in the bottle.
So not so much a question as a comment. One of the key things to take from this is we're looking at a different system. It's a different plant. So we're looking at barley rather than grapes, but it's still a plant system and it's responding the same way. It is making thiophenols during the malting process. And so when you malt, you germinate the plant, the grains by getting them wet. The smoke is the byproduct of the heat it takes to stop the germination to finish the malting process. But during that process, we're getting these thiophenols along with the volatile phenols in the malt. And then through brewing and through distilling, they're still there. And as MacKenzie pointed out, you're greatly concentrating them. So we're able to show in a separate plant system, the same kind of chemistry is happening as what we think is happening in grapes as well. So it's, it's essentially peaty scotches are just smoke tainted whiskeys. In a sense, but we don't look at them that way because that's the expectation.
Right.
Right. So there are some other differences, but at the end of the day, a lot of the aromas, and in fact, we use a peaty whiskey as one of our control samples when we're doing our analysis because it's a much more stable form and has many of the same compounds we're interested in. So it's kind of cool that we're seeing this in a different system, the same kind of chemistry.
And how long are they smoking the peat for? How long is that process?
It's a few hours. most of the uptake of the smoke happens in the first 2 to 3 hours of it. Once the grain dries, the surface of the grain dries, then it stops taking up these compounds from the smoke.
So should we just start marketing smoke tainted wine differently?
Well, I mean, it took the Scottish centuries to get that to be a standard accepted taste. And, you know, so if we have enough time.
I think I heard you say that the higher alcohol content of the whiskeys affects the partitioning of the thiols.
Yes.
How does that sort of provide any insight or implications if we consider wines with different alcohol contents? I mean, we're talking at dinner last night about maybe a new generation doesn't want as much alcohol in wines, and would this affect any smoke taint things as well? So.
Yeah, we're actually conducting a study right now to look at how ethanol affects extraction. So depending on from that study, we can look at the kinetics of the different volatiles and almost relate them to see how each one is affected. And from there, we can probably compare that to the different because we're looking at the same volatiles in oak that we do in smoke. So then we can compare that to the different ones that we use in smoke, the wine level. Would that make sense?
Yeah, so I think I heard ask you in a year.
Yes.
But again, it's the same chemistry, toasted oak and smoke. Or very similar.
Mine was sort of a comment too, because we had a great discussion at lunch, and we were talking about there's a group here that took their smoke tainted wine and distilled it. And I went along this, and it had those characters, and I was like, well, shoot, it should have those characters because that's Scotch. And I guess I didn't put that together. So distillation is not a remedial tool. Well, unless you clean it up afterwards,
I mean, it can be, I mean, distillation can be a way to separate these out, but not in a pot still.
Not in a pot still. I mean.
Okay, there we go.
Yeah, in a column still, you probably.
Yeah, and then you could activate a carbon and get it out. Yeah.
I have a question for you. So, given this body of work, if you were to stay on for another year or two, what would be your next set of experiments?
Well, I'm so glad you asked because I am actually staying on for this work. So I am working on additional methods to identify and quantify different sulfonated compounds, not just thiophenols, but other different sulfonated compounds. We're also going to be collecting smoke from wildfires to see how that works with our sorbent tubes. And it would be really interesting to evaluate the development of thiophenols and volatile phenols as they're exposed to grape kinetically.
Do you think you guys could just use the stunt malt as a way of doing this year round?
Yeah, no, it was a really fun process to be able to identify a different plant source that we can continue our research with without only waiting for that 3-month period.
This becomes analogous to the Pixie grape where
Yeah.
we look at malting
Not as cute.
year round and study some of the study the RNA transcriptomics and metabolomics associated with it in barley as opposed to grapes. It's not going to be identical, but there are going to be some very strong similarities, I think.